All right. I mentioned in the first video on exponential growth that there was this third kind of problem with Newton's law of cooling, and I'm going to give you an example of that it's a little bit different. There's a little trick you need to use here. You don't need to, but it really does make things a lot easier. So here's a problem: a bottle of pop at room temperature, 72 degrees Fahrenheit, is put in a refrigerator with a temperature of 44 degrees Fahrenheit. After half an hour, the temperature of the pop is 61 degrees Fahrenheit. I say pop because I'm from the Midwest and it irritates people who aren't from the Midwest when I don't say things like soda. Pop. It's pop. All right. So the questions we're going to be asked: one, what is the temperature of the bottle of pop after another half an hour? And how long does it take for the bottle to cool off to 50 degrees? So these questions are very much like what we had in the radioactive decay, the exponential growth problems. What we're going to need to do, though, is set up the model first. And setting up the model is a little bit different. So we know that, and this is Newton's law of cooling. It says that the change in temperature over time, and I know I've got big T and little t, but I'm going to get rid of that in a second, so don't worry about it too much. Big T, the change in temperature over time is proportional to the difference between the temperature of the object that's cooling and the outside temperature, or the surrounding temperature. Okay, so it's proportional to the difference, right? It's going to things cool faster in the freezer than they do in the refrigerator because the difference in the freezer is bigger. The difference between the temperature of the object and the freezer is bigger. And we can do our thing here with now we could do our usual thing with uh, what's it called, separation, to get a function for t temperature, and we can do that. The thing is, it's going to get a little confusing because of this part here, because of this t minus ts thing. So I'm going to do something else. I'm going to substitute a different variable in. I'm just going to make up another variable, and it's going to make things a little easier. I'm going to make up a variable called y, and y is just going to equal t minus ts. So y is the difference between the temperature, between the temperatures in the temperature of the object and the temperature of the surroundings. So I'm going to rewrite it like this: dy dt is equal to k times y. Okay, all I've done is replace, you know, replace y here, right, for t minus ts, and I can do that because I know that ts is constant, right? Ts equals 44 degrees Fahrenheit, right? That doesn't change, and I can do that over here because the change in the temperature is going to follow exactly the change in the difference in the two temperatures, right? They're going to go one to one. They're going to go with each other. So I can change it and rewrite it like this, and I get y equals y0 e to the k t. So I've got my familiar kind of equation here. And again, y is going to be the difference. Y is the difference in temperature. So I get, if I want to make this model here, I know that y0, the initial difference in temperature, is 72 minus 44, because the initial temperature is 72, and it's 44 degrees in the refrigerator, and when I do that I get 28. So I know y equals 28 e to the k t. And I know that, what else? I know that after half an hour, 30 minutes, the temperature of the pop is 61. So it's come down to 61 after 30 minutes. So that's going to be y at 30 is going to be 61 minus 44. Remember, this is the difference. It's not, y is not the temperature after 30 minutes. Y is the difference between the temperature of the object, the bottle of pop, and the temperature of the refrigerator. So at that point, after 30 minutes, that difference is 17. 17 equals 28 e to the k times 30, 30 minutes. Okay, now familiar, I can go solve for k. When I do that, I end up with k equals, and I'll take a little bit of a shortcut here, 28, sorry, not 28, too much of a shortcut, 17 over 28, all that divided by 30. And when I do that, I get roughly 0.0166. Negative 0.0166. K should be negative because the difference is getting smaller. The difference between the temperature and of the pop and the temperature of the refrigerator is getting smaller, right? Because it's cooling off. Okay, so we get a negative number. There we go. All right, so now we can actually approach. We can use this model to actually deal with some of these problems here. So change colors again. What do I got? Well, B says, or sorry, A. That's right, because there was no. A is, what is the temperature of the bottle pop after another half hour? So that's at T equals 60. Y equals what? How much has it changed then? Well, we know Y equals, what is it? 28, the initial difference, e to the negative 0.0166. And after an hour or 60 minutes, I did it in terms of minutes. You could have done it in terms of hours. And you get some number. What do you get? Y equals, this is the part where you want to be careful. I get Y equals 10.34. Now, be careful with this because that's, remember, Y is not telling us the temperature of the object. It's telling us the difference between the temperature. So it's telling us that 10.34 equals the temperature of the bottle of pop minus the temperature of the surroundings, which is 44. So we end up with T equals 54.34. You might get a slightly different answer depending on how you rounded it and so on, or if you rounded it or just left it as it was. All right, so let's do the last part here, C. And C is asking us, how long does it take for the bottle to cool to 50 degrees? So T equals 50. That means Y equals 50 minus 44 equals 6. So we're looking for the time when Y equals 6. So we'll have 6 equals 28 e to the negative 0.0166 t. We're looking for that t. We'll solve for that. To make a long story short, what's it going to be? Ln 6 over 28 divided by negative 0.0166. And it better be more than 60, I guess, because at 60 it had only gotten down. After 60 minutes, it was only at 54 degrees. I think it comes out to like 90 something. Oh, I get 92.8 minutes. I actually did this part. Okay, 92.8. All right, so there's your third example. It's a little bit more complicated. You have to do it a few times, and then you can see. You have to do it a few times and get used to, working with Y, the difference between the temperature of the object and the temperature of the surroundings, instead of working with just T itself. It is easier. You get yourself into less trouble. Otherwise, I don't know, it just gets confusing, I think. I would go with this way. All right.